Till now we have defined different types of convergence, as for example, for a sequence of random variables we have defined convergence in probability, convergence in distribution, convergence in pth mean or LP convergence, convergence almost surely, etc. We have also seen that convergence in probability implies convergence in distribution. So, the natural question is the converse true? That means, if a sequence of random variables converges to a random variable say x in distribution, does it necessarily imply that convergence in probability will also hold? So, the answer is not straightforward. In some cases we see that the reverse situation may not hold true. So, we will be discussing today some counter examples of such situations where convergence from one side may not imply the convergence from the other side. Also, we will discuss one extremely important theorem known as Statsky's theorem, which is related to convergence in distribution and convergence in probability corresponding to two different sequences of random variables. This theorem will be of extreme importance in statistical theory, in probability theory, and also in large sample theory. Convergence and related results too. We have seen the interrelationship between different types of convergence, as for example, convergence almost surely implies convergence in probability, which implies convergence in law. On the other hand, convergence in pth mean implies convergence in probability. So, the question is whether there is any other types of implication of convergence of one thing will imply convergence of other types and so on, which is not always true actually. So, we will now discuss a few counter examples to show that the reverse thing might not happen always. One first example is a convergence of law does not necessarily imply convergence in probability. So, let us consider the whole sample space omega as 0 1 and define a sequence of random variables x n omega as 1 if omega belongs to 0 to half and 0 if omega belongs to half 1. So, remember this 0 to half is semi open, half side is open and this is closed. Again we define capital X omega as 0 if omega belongs to 0 to half and 1 if omega belongs to half to 1. So, that means just look at some interesting feature that whenever x n takes the value 1, x takes the value 0, and whenever x n takes the value 0, x takes the value 1. So, this is a typical example that we are going to construct, and we define these two and this random sequence of random variables x n and x on the probability space, which is omega sigma field generated by the class of subsets of omega, which is B, and M, where M is the Lebesgue measure on the unit interval. Then it is clear that f n x equals to 0 when x less than equals to 0 and equals to half if x lies between x 0 less than equals to x less than 1 and 1 if x greater than equals to 1. And f x is also 0 if x less than 0, half if 0 less than equals to x less than 1 and 1 if x greater than equals to 1. So, immediately it is clear that f n x equals to f x for every x, but if we calculate modulus of the difference of x n minus x, which is exactly equals to 1, because x n would be 0 on the set where x n is 0, x is 1, and on the set where x n is 1, x is 0. So, modulus of the difference is always 1. So, modulus of x n minus x is 1 with probability 1 for every n equals to 1, 2 and so on. So, this shows that although we have convergence in law for this example, but convergence in probability does not hold good. So, the next one we will discuss convergence in probability does not necessarily imply convergence in almost sure convergence. So, let us consider a sequence of IID random variables, say y1, y2 and up to yn. Then xn equals to yn by n converges in probability to 0, which is trivial, because since yi's are IID random variables, then probability mod y1 greater than n epsilon goes to 0 as n goes to infinity for every epsilon greater than 0. So, fixing every epsilon positive epsilon. But xn converges to 0 almost surely, if and only if. So, the question is, when we can say that xn converges to 0 almost surely? Only when expectation of mod y1 less than infinity. This follows from Kolmogorov's strong law for IID random variables. We will discuss this in more detail later on. So, convergence in probability might imply convergence in convergence almost surely, provided this condition, this existence of first order moment should hold, that means expectation of mod y1 less than infinity. Now, for example, take y1, y2, yn are IID Cauchy random variables, and we know that for Cauchy random variables expectation of mod of y1 is not really less than infinity. So, although xn converges to 0 in probability, but xn does not converge to 0 almost surely. So, this is a nice counter example to show that convergence in probability does not necessarily imply convergence almost surely. Next one, we have seen using Markov-Chebyshev's inequality that convergence in LP or convergence in pth mean always imply convergence in probability. So, let us investigate whether the other way around is the reverse direction is also correct or not. Unfortunately, the answer is it is not, it does not always hold good. So, we are discussing one counter example to show that this is not necessarily true. So, let us define xn as a random variable which takes a value n with probability 1 by log n and 0 with probability 1 minus log n. Then as n goes to infinity, it is clear that log n goes to infinity, that means 1 by log n goes to 0. That means xn is xn, probability xn takes the value n goes to 0 as n goes to infinity. So, that means probability xn takes the value 0 with probability 1. So, xn goes to 0 in probability. Now, consider any p greater than equals to 1, we can also take p little less than 1 also, but positive. So, expectation of mod of xn to the power p, if we just calculate this thing, we will get this is n to the power p by log n, and naturally this goes to infinity as n goes to infinity. So, here we see that expectation of mod xn to the power p goes to infinity, that means it does not converge in LP, but probability mod of xn less than half equals to probability xn equals to 0, because even for n equals to 1 this takes 0 or 1, n equals to 2 this takes 0 or 2 and so on. So, when mod xn less than half, it satisfies only one value of xn, that is xn equals to 0, which is 1 minus 1 by log n, and this goes to 1 as n goes to infinity. Now, just instead of taking half, we can take epsilon. So, just take epsilon equals to half, we get xn goes to 0 in probability. So, this implies that we have a sequence of random variables which does not converge to x or to some random variable in LP, but it converges in probability. Next one, let us consider one example where we will demonstrate that convergence almost surely will not necessarily imply that convergence in LP. So, again let us consider a probability space as omega b and m being the Lebesgue measure on omega, which is 0 and 1, 0 to 1 interval, that is the unit interval, and xn omega equals to e to the power n if 0 less than equals to omega less than equals to 1 by n square and 0 otherwise. So, for p greater than 0, if we calculate expectation of mod xn to the power p, this is e to the power n p by n square, which goes to infinity. That means, it does not converge in LP, but using Borel-Cantelli lemma, we can immediately show that x n goes to 0 almost surely, because if we calculate this probability sum over n greater than equals to 1, probability mod x n greater than epsilon, this is equals to summation n greater than equals to 1 into 1 of 1 by n squared, which is a convergent series actually. So, this is less than infinity. So, that means x n converges to 0 almost surely, but it does not converge to in LP or in pth mean. Another example is an example of convergence in pth mean, but not almost everywhere. So, both if we cannot think of one implies the other in respect of LP and S convergence. So, let us consider one example again, omega as 0 1 and x n m omega as 1 if m minus 1 by n less than equals to omega less than equals to m by n, m equals to 1 to n and n equals to 1 to and so on, 0 otherwise. So, clearly expectation of mod of x n m to the power p equals to, just calculate this probability, it is nothing but 1 by n, which goes to 0 as n goes to infinity. So, this means that convergence in LP is here for this sequence x n m. Now, we arrange this double sequence, because x n m there are two suffixes, double sequence in a single sequence, and arrange the sequence as x 1 1, x 2 1, x 2 2, x 3 1, x 3 2, x 3 3 and so on. And we will see that this converges to 0 in pth mean and hence in probability. So, this sequence convergence in probability by one earlier result. Now, for any omega not equals to 0, the sequence x n m omega has infinitely many zeros and infinitely many ones. Thus, the set on which x n m converges has probability 0, and hence we can immediately say that x n m does not converge almost surely. So, now we come to the famous theorem due to Slutsky, which says that x n converges to x in distribution, y n converges to c in probability, then x n plus y n converges in distribution to x plus c. Now, what is the meaning of x n plus y n converges in distribution to x plus c? Means that the distribution function of x n plus y n tends to f of x minus c at each continuity point of f. Similarly, x n y n product of these two sequences of random variables converges in distribution to c into x, that means distribution function of x n y n tends to f of x by c at each c f, and x n by y n converges to x by c in distribution, that is a distribution function of x n by y n tends to capital F of c x at each continuity point of f. Let us give a brief outline of the proof. The proof is very similar, the technique is similar to the proof. If you recall, convergence in probability implies convergence in distribution. Proof is very similar to that. So, let us consider one epsilon which is greater than 0 and choose x such that x minus c plus epsilon, x minus c minus epsilon, they are all continuity points of f. Since epsilon is arbitrary, we can have this liberty to choose this as continuity points. Now, consider f of x n plus y n x, that is the distribution function of x n plus y n, which is nothing but probability x n plus y n less than equals to x. Now, we introduce one event which is mod of y n minus c less than epsilon and apply the simple theorem on probability, that is probability A equals to probability of A intersection B plus probability of A intersection B complement. So, we get immediately probability x n plus y n less than equals to x, comma mod of y n minus c less than epsilon plus probability x n plus y n less than equals to x, comma mod of y n minus c greater than equals to epsilon. Now, again, since we know that A intersection B probability of that is less than equals to probability of B, we can immediately write that this entire quantity is less than equals to the first term plus we can replace this second term by probability of mod y n minus c greater than equals to epsilon. Again, from the first term we can see that this is a subset of x n less than equals to x minus c plus epsilon. So, this is less than equals to probability of x n less than equals to x minus c plus epsilon plus probability of y n minus c greater than equals to epsilon. Now, probability of now if we take the lim sup on both sides, we get lim sup of f of x n plus y n x less than equals to lim sup of probability x n less than equals to x minus c minus epsilon plus lim sup of probability y n minus c greater than equals to epsilon. The last term goes to 0 as y n converges to c in probability. So, hence we can get lim sup of f of x n plus y n x less than equals to f of x minus c plus epsilon, because we know x n converges to x in distribution for every epsilon greater than 0. Again, starting with probability x n plus y n greater than x and proceeding similarly, we have f of x minus c minus epsilon less than equals to lim inf f of x n plus y n x. So, similarly 1 and 2 gives us that since x minus c is a continuity point of f and epsilon greater than 0 may be taken to be arbitrarily small, so that x minus c minus epsilon, x minus c plus epsilon, they are all continuity points of f, and obviously epsilon is arbitrary, then 1 and 2 gives us limit of f of x plus x n plus y n of x, that is limit of the distribution function of x n plus y n as n goes to infinity equals to f of x minus c, which that is same as saying x n plus y n converges to x plus c in distribution. Now, proceeding similarly, we can prove b and c. B means product of the two variables will converge to in distribution to c into x, and x n by y n converges to x by c in distribution. So, this gives us the proof of Statsky's theorem, and this is an extremely important theorem in statistical theory, in probability as well as in large samples, especially in large sample inference. So, we have seen in this class that although convergence in probability implies convergence in distribution, and we know that convergence in distribution implies convergence in probability only when it converges to a degenerate random variable that is a constant. But otherwise, this reverse convergence, reverse way, that means convergence in distribution, whether it implies convergence in probability does not hold good always. So, we have given one counter example to show that this may not hold. Similarly, although we know that convergence almost surely implies convergence in probability, but the reverse may not happen. So, we have also given one counter example, and the most important thing that we have learned is the Statsky's theorem. The implication of Statsky's theorem is that if we have a sequence of random variables that converges to a distribution, convergence in distribution to another random variable, and we have another sequence of random variable that converges in probability, can we combine or can we generate some function of these two sequences of random variables which will converge to another random variable, might be related to the original random variables in which these two sequences converge, and what is the mode of convergence. Now, it is seen that the final convergence is basically convergence in distribution, and it is immediately clear that it has an immense importance, especially in large sample theory or statistical inference, especially when the sample size is large, because we might have one statistic which converges in law to say normal distribution, and we have another statistic which converges in probability to some function, maybe some parameter or a function of a parameter. Then we can combine these two to get the convergence in distribution of a random of a nice statistic, and the limiting distribution is very simple. Actually, it can be shown that the standard t-test, in case of large sample, we can approximate this t-test by a large sample normal distribution or a standard normal test. Similarly, this will help us to tackle the famous Fisher-Behrend problem, and actually application of Statsky's theorem indicates that Fisher-Behrend problem can be tackled when the sample size is large in a very simple, in a much easier way, and the resultant distribution is nothing but a standard normal distribution, obviously sample size should be large.